All right, welcome to today's explainer. We're going to take a pretty wild journey through the world of metals and nonmetals. We'll start with the tangible stuff, the things you can actually touch every single day, and then we're going to dive all the way down to the invisible atomic bonds that completely define them.
So, here is our roadmap for today. We're going to cover 1. Physical properties explained, 2. Exceptions to the rules, 3. Chemical reactions of metals, 4. The reactivity series, and finally, 5. Exploring the atomic level. Starting off with Section 1, Physical Properties Explained, or the Observable World. Let's ground ourselves in the macroscopic traits of pure metals and see how they shape the physical environment around us.
Now, metals aren't just rigid, stubborn blocks. They have this incredibly unique ability to be hammered out into extremely thin sheets, which is what we call malleability, or stretched into thin wires known as ductility. This flexibility is absolutely crucial because it means we can basically bend nature to fit our human needs. To really wrap your head around the sheer scale of that ductility, just look at gold. Gold is so remarkably flexible that a tiny 1-gram nugget, like literally something that would just sit right on the tip of your finger, can be stretched into a wire 2 kilometers long. Seriously, it's just mind-blowing.
And this isn't just abstract science. These fundamental properties dictate the stuff you use every single day. We use aluminum and copper for our kitchen pots because, well, they conduct heat beautifully. We rely on copper for electrical wiring. And because metals are sonorous, meaning they produce a ringing sound when struck, they're the exact reason a school bell can cut through the noise of a crowded hallway.
Moving on to Section 2, Exceptions to the Rules. Chemistry is full of super strict rules, for sure, but as you'll see, the anomalies are what truly make the subject captivating.
So you'd probably think all metals are hard solids, right? But rule breakers totally upend that assumption. Take mercury, for example, which actually flows as a liquid at room temperature. Or alkali metals like lithium, sodium, and potassium. They're physically so soft because of their low densities and melting points that you can literally slice right through them with a butter knife.
And the exact same thing happens on the flip side of the periodic table. Nonmetals are usually these dull insulators, but nature always leaves room for a few surprises. Iodine has this beautiful lustrous shine. Diamond, which is an allotrope of carbon, is literally the hardest known natural substance. And graphite, it effortlessly conducts electricity.
Let's dive into Section 3, Chemical Reactions of Metals. We're leaving the physical traits behind now to observe what actually happens when we force these metals to react with the world around them.
When metals burn in air, they don't just melt down into a puddle. They actively, chemically combine with oxygen to form completely new compounds called metal oxides. And the visuals here can be stunning. Magnesium, for instance, burns with a dazzling, almost blinding white flame. Copper doesn't burn with a flame at all, actually. Instead, it gets coated in this thick black layer of copper-2 oxide.
Now let's talk about water, because this is where we see a massive escalation. Metals like lead, silver, and gold do absolutely nothing in water. But if you drop a piece of sodium into a simple glass of cold water, you get a violently explosive exothermic reaction where the evolved hydrogen gas instantly catches fire. Meanwhile, calcium and magnesium are a bit more chill. They form hydrogen bubbles that act like tiny life rafts, literally causing heavy pieces of metal to float.
And we see this exact same hierarchy play out with acids. When a metal reacts with a dilute acid, it produces a salt and hydrogen gas, but the intensity is all over the map. Magnesium will bubble furiously and heat up a test tube of dilute hydrochloric acid, while a piece of copper sitting in that very same acid will just sit there completely unchanged. No bubbles, no reaction, nothing.
But here's the ultimate cheat code. I just said some metals totally ignore acids, and gold is famous for that. However, if you mix concentrated hydrochloric acid and concentrated nitric acid in a 3-to-1 ratio, you create this highly corrosive fuming liquid called aqua regia, which is Latin for royal water. This specific cocktail is one of the only reagents on the planet that can completely dissolve solid gold.
All right, Section 4, the reactivity series. All of these tests we've been talking about naturally lead us to officially rank these elements into a definitive chemical hierarchy. This definitive order is known as the reactivity series. Think of it as chemistry's ultimate power ranking. It places the supervolatile potassium and sodium right at the top of the throne, scaling down through the moderately reactive iron and firmly placing stable, completely unbothered gold at the very bottom. Because potassium and sodium are the reigning champs at the top of this list, they are incredibly dangerous. They are so aggressively eager to react with just the oxygen and moisture in the open air that simply leaving them out on a table will cause them to spontaneously catch fire. To keep them stable, they literally have to be submerged and stored in kerosene oil.
And this hierarchy isn't just a passive list on a chalkboard, it's strictly enforced in nature through displacement reactions. If you drop a highly reactive metal into a solution that has a less reactive metal in it, the powerful one will literally kick the weaker one out of its chemical compound and take its spot. It is a microscopic game of chemical musical chairs, and the strongest always wins.
Finally, Section 5, Exploring the Atomic Level. We've observed the what and the how, but to finish up our explainer today, we need to zoom down past what the human eye can see to figure out the invisible why.
I mean, seeing a chunk of sodium explode in water or magnesium burn with a blinding light is a really thrilling observation. But we have to ask ourselves, why do these specific elements behave with such extreme, almost frantic urgency, while others, like gold, do absolutely nothing?
Well, it all comes down to electrons. Every element in the universe is basically desperately trying to achieve a perfectly stable, completely filled outer shell, exactly like the unreactive noble gases. Metals happen to have just a few extra dangling electrons, while nonmetals are agonizingly close to being full.
So this creates the ultimate chemical partnership. Look at sodium. It is desperate to get rid of just one single electron. Now look at chlorine. It's missing exactly one electron. When they meet up, sodium eagerly hands its electron over, and chlorine happily takes it. It's a perfect match.
The exact moment that single electron transfers, something incredible happens. We now have one positive ion and one negative ion. And just like magnets, opposites attract. They lock together with a massive, invisible electrostatic force, creating an entirely new substance, an ionic compound. Like sodium chloride, which, is exactly the same regular table salt you probably have sitting in your kitchen right now.
But they don't just form one tiny little pair. These ionic compounds lock together in these massive, repeating, highly structured 3D aggregates of electric charge. Because this electrostatic attraction is so profoundly strong, ripping these structures apart requires a huge amount of energy, which is exactly why ionic compounds have such incredibly high melting points.
Which leaves us with this final thought for today's explainer. If something as infinitesimally tiny as a single electron completely dictates the reality we can see, touch, and use, deciding whether an element violently catches fire in your bare hands or beautifully conducts electricity to light up your home, what other invisible, microscopic rules are secretly building the macroscopic world around you right now? Something to think about. Keep questioning, keep observing, and we will see you in the next one.